Hi, I'd like to go through an example of using vector addition diagrams to solve a problem for an object experiencing unbalanced forces. So I'm going to do this problem with a child takes a trip down a 3-meter long slide. The frictional force on the child is 160 newtons, and the child has a mass of 30 kilograms. Now, the first step in this problem is going to be to draw my free body diagram. I like to start with the force of gravity, which always goes straight down. Now I know the force of gravity is m times g, and we're given the mass of this child is 30 kilograms. And I know that near Earth's surface, g is always 10 newtons per kilogram, which means the force of gravity on this child must be 300 newtons. Now, for these next forces, I'm going to just add a dashed line to represent the surface of the slide. That helps me keep track of direction. Now, I know this child is compressing the surface of the slide, which means that there must be a normal force perpendicular to the surface of the slide. I also know, because the problem tells me this outright, that there is a force of friction of 160 newtons on that child. I know that as that child makes their way down the slide, they must be shearing the surface of the slide, which is why that force of friction must be pointing upward. And I'll go ahead and add in that angle of 55 degrees. Something I'm going to make a note of, because I'll need to use this information later, is that if I were to draw a horizontal line up there, there would also be an angle of 55 degrees between friction and that horizontal above. The next thing I'm going to do is draw my vector addition diagram, which is essentially just my free body diagram rearranged. I like to start with the force of gravity, which is just straight down. Now I'm going to do my normal force. I'm going to go ahead and assume that since it gave us the value of the force of friction, that the forces on this child are unbalanced. And so that force of friction is not going to quite close this shape. And this leftover chunk is my net force. The next thing I'm going to think about with my vector addition diagram are angles. So first up, I can see on my free body diagram that there must be a 90-degree angle between the normal force and the force of friction. Since the normal force goes right along, or goes perpendicular to the slide, and the friction force goes along the slide. Next thing I'm going to use. So that net force must be along the same angle as the force of friction, which means that it must be 55 degrees below the horizontal. What that means is that this angle right here inside of the triangle must be 35 degrees, since 35 plus 55 is 90, which means this angle down here is 55 degrees. So now I've got a triangle where I know one side and I know all three angles. I can start doing some trig to figure out some of these other forces. I'll go ahead and start with the normal force. I'm going to use this 55-degree angle, though I could use either. That normal force is adjacent to the 55-degree angle, which means that it must be equal to Fg times the cosine of 55 degrees. So if I do 300 newtons times the cosine of 55 degrees, when I put that into my calculator, I get 172 newtons. So that must be my normal force. And I like to go ahead and add those numbers to my vector addition diagram as I figure them out. Next, I'm going to find the net force. So the net force plus the force of friction must make up this side of the triangle. Well, that side of the triangle is the force of gravity times the sine of 55 degrees. So if I do that minus the force of friction, that should give me my net force. So if I do 300 newtons times the sine of 55 degrees minus 160 newtons, when I put that into my calculator, I get 85.7 newtons. So that must be my net force. Another thing I can find once I know the net force is the acceleration of this child, since acceleration is net force over mass. So I can do 85.7 newtons divided by 30 kilograms to get an acceleration of 2.86 meters per second squared. Now in this particular problem, we happen to know how long this slide is. So I'm going to go ahead and figure out how long will it take the child to get down this slide. So if I do a quick velocity versus time graph, I know this graph must have a slope of 2.86 meters per second squared. I also know, since the slide is 3 meters long, that must be the area of this graph. And then the base of the triangle made by this graph is the time. And the height of the triangle made by this graph is the change in velocity. So I can say acceleration is change in velocity over time. Now both of these are unknowns, so I'm going to go ahead and just solve this for delta v. So I can say delta v is acceleration times time. If I work from the area of the graph, I can say the area is the base of the triangle times the height of the triangle divided by 2. I'm going to go ahead and replace delta v with acceleration times time, which gets me that the distance traveled is acceleration times time squared over 2. If I do a little algebra to get t alone, I'm going to solve for the time it takes this child to go down the slide. I can do 2 times delta x over a equals t squared, which means when I plug in numbers, if I have 2 times 3 meters over 2.86 meters per second squared, and then I take the square root of all that, when I plug that into my calculator, I get that the child will take 1.45 seconds to get down the slide. So there we go. That's an example of how we can use vector addition diagrams to solve a problem where the forces are unbalanced.